Hi, I'm Chris Mawata. I've been a learning tree instructor since the year 2000 and have written more than 40 courses for Learning Tree. I've also worked as a professor of mathematics at the University of Tennessee at Chattanooga and published papers in mathematics, machine learning, and visualization. Today, I want to talk to you about using supervised machine learning techniques for anomaly detection. So what are supervised anomaly detection techniques? Well, we have several different algorithms that we can use. We have decision trees, which will be really a divide and conquer kind of approach, where we try to iteratively use different attributes of our data to break it up into subgroups that get purer and purer. You can imagine if someone was trying to figure out if a mushroom was poisonous or not poisonous, they would look at different attributes of the mushroom and say, all right, I see a brown cap, so probably it is edible. Or I see the gills are black, and you say, maybe I'd better not eat that, and so on. We shall talk about support vector machine, where this time our algorithm will try to draw a boundary between our data items, where the items on one side are going to be of one classification and on the other side will be of another classification. And then, of course, these days we have neural networks which are going to try to learn. We'll talk more about what that learning entails from data that we have already labeled to figure out how best to decide whether our data is normal or abnormal. So when we talk about supervised anomaly detection, because it is using supervised machine learning, we're going to need data that is already labeled by human beings as normal or abnormal. So in the case of the decision tree, we start off by saying which of our attributes, so imagine you've got attributes like the color of the cap of the mushroom, the color of the gills, the height of the stalk, where the mushroom was found. Or maybe your problem is to look at attributes of people applying for a loan, and you're looking at things like how long that person has been at their job, how much they earn, how much they spend on food, how much they spend on accommodation, and so on. Try to pick the one that best splits your data into the different categories. People who will pay back the loan, people who will maybe not pay back the loan, mushrooms that are poisonous, mushrooms that are maybe edible. Using just one attribute will most likely not give you a perfect split. So you might say, okay, so after the first split, let's split it further using another attribute. So I've split my data based on the color of the mushroom cap. Let's split it based on the color of the gills, and so on. So each time your subsets get purer and purer and purer. But you need to know which decisions are going to lead to that. And the way that you build the tree is to start off with labeled data so that your algorithm knows when it is correct and when it is not correct. So we have several places in the curriculum where we talk about this. And for a deeper dive, you can join our training classes to learn about the different things that go on inside of a decision tree algorithm. So you can build a decision tree for any classification problem. In our case, classifying our data as normal or abnormal. And what you want is later on, when you have data that you haven't yet classified, that decision tree will help you to classify it as normal or abnormal. Now, another thing that is often done, again in the decision tree arena, is to say, how about using several decision trees, maybe hundreds, maybe thousands. Every so often you'll see tens of thousands of decision trees. And the idea is to create an ensemble of trees that collectively is stronger than a single tree. Now you might say, is it going to be the case that multiple not so skillful trees are able to beat a single very skillful tree? In most cases, yes. But remember that if you're going to build multiple trees, it's going to be more costly in terms of computer resources, but you generally get better results. And the way to think about it is, if you have someone who is very, very good at chess, you often see them challenging a group of other chess players and simultaneously playing against them. Now, when you have many weaker players, individually they can't beat the very good player. But if those weaker players are trained differently, then it's very likely that one or two of them will spot the move that would get them to gradually get better and better and eventually beat the very good chess player. So collectively, the ensemble is going to be stronger than the single strong tree as long as they are different. So how do I get 10,000 trees that are not identical? Well, one way to do it, which is the bagged trees approach, is to say, I have so many records. Let's say you have 1 million records. Why don't you train a tree on just 100,000 of them so it doesn't see the rest? Train another tree on a different 100,000 records, and so on. So each tree does get 100,000 records, but a different 100,000 records. And so each tree will be slightly different from the other trees. So you get, let's say, 10,000 trees, but they won't be making exactly the same decision. So then you make them vote. I have a new record. I give it to my 10,000 trees, and maybe 9,000 of them say, this is normal. And 1,000 say, this is abnormal. And then I'll say, okay, I'll take the normal because that's the majority of my trees. Another time, if a majority say this data is abnormal and only a minority say we think it is normal, I'll go with the majority. Now, in real life, it gets more fancy because very soon your algorithm recognizes which trees are stronger than others. So some trees actually get more voting power than others because they turned out to be better. So that's one way to do it. Another way to do it, which is how random forest work, is to say, all right, we'll give each tree a subset of your data records. We'll give them so many records out of your 1 million records, but we shall also have another restriction. We shall only show them some of the attributes. So imagine you have, say, 50 things that you know about the people trying to get a loan. Maybe tree 1 will get to see 20 of those attributes, so it doesn't know about the others, which means it will be a different tree because it's trying to use these few attributes as best as it can. Then another tree will see another 20 attributes, a different 20 attributes, randomly chosen. That's where the random in random forest comes from. And it will do the best it can with the 20 you give it, and so on. So with random trees, you have both the idea of giving them only some of the training records, so they don't get to see everything, and only giving them some of the attributes. You end up with trees that are different, not as strong as the strongest tree you could have built, but collectively, they turn out to be stronger. Another way you can do it, which is the idea of boosted trees, is to say, let me first train one tree with my data. It will make some mistakes. Let me train a second tree, and remember that the trees try to divide the data so that it is as pure as possible. This time, add in a penalty and say, I want you to try to get the best score you can, but it's not just going to be making the subsets as pure as possible. I'm going to penalize you every time you make the same mistake with a data item that the first one did. So let's say the first tree mistakenly said a certain record was an anomaly. Well, the second tree had better not, because if it gets that same mistake, if it makes that same mistake, then you're going to penalize it. And as you go further down, the third tree is going to get a boosted penalty. That's where the boosted comes in. So first one gets it wrong, second one will get a penalty. If the second one gets it wrong again, the third one had better not, because it's going to get a boosted penalty. So it gets more and more expensive as you go further down, as you have more and more trees being trained. It becomes really expensive to make that mistake. So you get a series of trees that are designed to compensate for the mistakes of the trees that were trained before them. A very famous version of that, XGBoost, the XG is talking about the way that it calculates that boost in the penalty. XGBoost is extremely popular because it turns out that it makes a nice collection, a nice ensemble of trees that collectively are very, very good at doing classification. Another approach is the support vector machine approach. So how does that work? Well, this time, what the algorithm tries to do is to try to cut a path through your data in such a way that the distance between that path that it is creating and the different categories of data, in our case, we're looking at normal data versus abnormal data, is as big as possible. So you can see in our diagram, we have the line going between the blue points and the black points, and those arrows are showing the distance from the line to the closest blue point or to the closest black point. Sometimes you get a draw, like you can see there are two blue points the same distance away from the black point, the black line. And in that way, you can get essentially a division of your data into, in our case, normal and abnormal data. Now, this is a rather synthetic example because we have a nice straight line dividing our data. Remember that in reality, you typically have very many attributes. So it's not a two-dimensional problem where you can, draw it on a page and you see all the details. Instead, you have a multi-dimensional problem. And also, the surface that divides the data best will probably not do a perfect job like ours is doing, and probably will not be straight. So here, for example, we're going to look at data that is taken from the medical world, and it is looking at tumors. And when they look at tumors, they have very many attributes, the size of the tumor, the texture, the softness or hardness of the tumor, etc. So we're just looking at two of them. We're looking at the mean radius and we're looking at the texture. And you can see in the blue area, those are the ones that we're going to consider to be normal. And in the area outside of that yellow boundary, we have the ones that we consider to be abnormal. Okay, so support vector machine tries to essentially separate the data that you're going to consider to be normal from the data that you're going to consider to be abnormal. Well, of course, we have the neural networks. One architecture for neural networks is called the feed-forward neural network, and they're very good at classification. We want to classify our data as normal or abnormal. The way that feed-forward neural networks work is really from left to right, in the sense that you have your data coming in as inputs, and it is fed to some neurons. So the green circles represent your input nodes, the neurons that get the data. And then we try to create a weighted sum of our data. Think of it in terms of some attributes. So somebody says, is this person going to be a good loan? You're going to say, well, I have some attributes, how much this person earns, how long they've been at their job, how much money they spend on accommodation, etc. And I'm going to put those together. But some are more important than others, so I'll give them a bigger weight. Some are less important than others, I'll give them a smaller weight. Now, that data and the results of those calculations are then passed on to more neurons. So you get layer after layer after layer. Now, the layers that come after the input layer are often referred to as hidden layers because they don't see the fresh inputs, they see the calculations of the layer before them. At the end, you will have an output layer. In the case of doing anomaly detection, our output layer will have one node because we want it to give us a conclusion. Is this data normal or is it abnormal? So you get a prediction. Essentially, you will get something like, I am 20% sure that this data is abnormal and 80% sure that it is abnormal, and so on. So you come to a conclusion. But then remember, we're using data that has been labeled as we're training. So during training, why don't we take that conclusion and compare it with the known outcome? Now, this is the label that the humans put on the data. So you compare the two. Of course, the hope is that they match. At the beginning, the chances are that they won't match. And so you're going to look at the difference between your prediction and the known correct answer. So let's suppose it turns out that your conclusion is incorrect. Well, how far away are you from correct? In other words, how big is the error? So you calculate how big that error is, and then you want to say, why don't we adjust those weights? Remember, we were talking about having weights that indicate which of our data is going to be more significant than other data. Why don't we adjust those weights so that next time we're more likely to get this question correct? And that's the fault learning part of our training. So your model learns by looking at the examples you've given it and trying it out, looking at the error it gets, and then figuring out what adjustments to the weight in the different nodes would make it able to get a better answer. Okay, so we've seen three different approaches to supervised anomaly detection. We've talked about decision trees, which is really a divide and conquer type of approach. We've looked at support vector machines, where we're trying to slice our data into two chunks, part that we're going to say is normal, the part that we're going to say is abnormal. And we've seen that we can use neural networks, where essentially we have a model that learns what weights to assign to the different attributes that we have in our data and come to a conclusion as to whether it is normal or abnormal. So now that we know about supervised anomaly detection techniques, please join us for more content on anomaly detection from Learning Tree International. Well, of course, we have the neural networks. One architecture for neural networks is called the feedforward neural network, and they're very good at classification. We want to classify our data as normal or abnormal.